very happy to have Vivek here from San Francisco. He's with Google Health, worked on projects like Mpom and Mpom 2, and also worked at Meta AI Research before that. So with that, Vivek, let's dive in. Thanks.
Hi everyone, great to see all of you over here. As Nathan said, I am a research scientist at Google, where I lead research at the intersection of large language models and biomedicine. So a bit more about me. I like to call myself a product of the MOOC revolution, massive open online courses. My undergrad degree was in hardware engineering, and I knew absolutely next to nothing about AI and ML. But one day, while browsing the internet on whatever little bandwidth I was getting access to in my undergrad lab, I stumbled onto Professor Andrew Ng's course on Coursera, and I was absolutely hooked onto that topic. The idea of building systems that can learn was utterly fascinating to me. And since then, I've been trying to do everything I can to learn about this topic and work in this field as much as possible. So I went to UT Austin for grad school, and UT is probably not like Stanford, where there is a paper on archive and 3 months later there is a course on the topic. But it still had professors who gave a lot of good grounding on classical machine learning topics, expert system, Bayesian systems, old school reinforcement learning, and so on and so forth. So that was great, but I was incredibly fortunate to end up at Facebook AI after grad school, where I was one of the early engineers, and I got to work at the intersection of both research and production, and so worked in a bunch of different problem domains, ranging from speech recognition, natural language processing, conversational AI, computer vision, and while doing that, I was seeing not only where using deep learning, we were able to smash research benchmarks, long-standing problems and grand challenges, but we were also building products with magical new experiences and lifting key metrics such as engagement on newsfeed, revenue on ads by margins never seen before. So this thing clearly was working. So the question I was asking myself was, where is now AI going to have the most impact? So besides access to education, which completely changed my life, the other recurring theme was access to healthcare. So I grew up in parts of India where, for most people in the nearby towns and villages, going to see a doctor was simply not a possibility. It meant like walking 30, 40 miles in extreme heat, often giving up on a day's wages or going without food. And so I knew several people who did not see a doctor in their lifetimes. And this meant, not catching diseases that were preventable, adverse life outcomes, and generally overall lower life expectancy. So I always wanted to do something about this. So my undergraduate thesis was a fairly rudimentary app, but an app called Ask the Doctor Anytime, Anywhere. So the name kind of tells you what we wanted to do about it. It was built using classical machine learning systems, by which I mostly mean a lot of rules and a bit of SVMs. The technology was not there 10 years back. But I'm delighted to say that the arc of progress in technology, and AI in particular, allows us to dream of that future again, a future where we can scale up access to healthcare, world-class healthcare to everyone, and put a world-class AI doctor in the pockets of billions worldwide. And so today, I'm going to tell you more about a couple of projects that we have been working on at Google over the last year, which I believe are important milestones towards that. So the first one is our work on Mpom. And if I were to say that we were the first to do large language models for biomedicine, that's a total lie. There's been plenty of people who have been doing this, especially since transformers came online. But what's been missing is, I would say, one, benchmarks, and two, evaluation frameworks. So in many ways, what I would say, besides the invention of transformers, what catalyzed progress in LLMs over the last few years, I would say it's probably benchmarks such as Big Bench and MMLU, which is another one. But there was nothing similar for that, just like that for medicine. And then the second thing is evaluation framework. And I will come back to this a little bit more in detail again. But I've been working in medical AI for several years. We have a big team at Google which has been doing this for several years. And we clearly know that the metrics that you use to optimize machine learning models And in case of large language models over here, your log likelihoods, or like multiple choice accuracy or NLG metrics such as Blue and Cider, they are not reflective of utility in real world clinical workflows. So you need to go beyond that and come up with evaluation frameworks that assess the utility of these models in real world application settings. So I would say these were the two key things that were missing. And so we decided to do something about it. So the first question was, okay, what is the task on which you're going to assess these large language models? And so for that, we decided to use the medical question answering task. And this is because answering a medical question answering often requires strong comprehension ability, the ability to recall medical knowledge, and then reason and manipulate about it to come up with the right answer. And this answer has to be legible and understandable to the end user, which can be an expert doctor, or it could also be like a lay user. And then the second thing is question answering is also very general, and it subsumes many different application scenarios. So you can frame many different tasks, such as summarization or triaging of patient concerns or clinical decision support. All of them can be framed in this question answering framework or like instruction answer framework. So that was the task we decided to anchor on. But the next question was, okay, what data sets do you want to use? And so when we were looking at the data sets in the field, we saw many of them, and these were all assessing different model capabilities in different settings. So we decided to bring all of them together and curate this one big benchmark called Multimate QA. And so this benchmark spanned professional medical questions, which were used to assess doctors and clinicians, but it also had medical research questions from papers in PubMed and beyond. And the last thing is often like lay users come to search engines such as Google and ask for medical information. And so we also wanted to cover that scenario as well. So there's a diverse range of topics that we were covering over here. And in terms of the kind of answers that we wanted the model to produce, it included multiple choice answers, but it also included long form answers over here. And again, some of the questions could be open domain, where the knowledge base from which you're going to answer is going to be the entire internet, and some would be more closed domain. So that was the benchmark that we used, but one of the limitations that we saw was for data sets pertaining to consumer medical questions, there wasn't like big or rich data sets, so we decided to contribute our own, and that's what we call Health Search QA. It's a data set of questions which are commonly asked by users on Google pertaining to medical information. So we have the task and the benchmark. So here are a few examples again. So you can see questions from Health Search QA, which is common questions on Google, and then on the right you see the USMLE questions, which often contain like a vignette with like very detailed symptoms about patient history, and then you have to like combine that information with other information that you may know or not know about, and then come up with the final answer. And this all often involves like a process of elimination, where you have to like figure out and use like uncertainty to come up with the right answer over here. So we have the task and the benchmark, and the next question was how to evaluate. And as I said, like the objective metrics that you use, such as NLG metrics like Blue or Cider or multiple choice accuracy, they don't cut the teeth over here. So we needed like human evaluations. And to do that, we decided to come up with this framework where we would have expert clinicians assess the model responses. And we saw that there were multiple different axes that we needed to evaluate these responses on. And so those included like hallucinations, and so that's what we call agreement with scientific consensus. Then we also needed to look at like the possibility of harm or bias in these answers, and also evidence of like the ability to comprehend the question, retrieve the right appropriate medical knowledge, and then reason about it. So there are multiple axes over here, but we wanted very granular feedback so that we can properly assess these models. But while doing that, we also realized that the end users of these systems are not always going to be doctors or clinicians. They are also going to be lay users, and for them, what matters more is how helpful and how actionable the insights the model producers are. So we also wanted to capture that, and so we had a separate evaluation framework where we had lay users, non-expert users, assess the model responses. So we have the task, benchmark, and the evaluation framework. And so now the fun part, which was the modeling. And so to do that, we decided to build on top of the shoulder of giants at Google. And so we already had access to the Mpom model, which I think is still to date the largest publicly announced densely activated decoder-only LLM. We also had access to an instruction-tuned variant at that point of time, Mpom, which was state-of-the-art on many natural language processing benchmarks at that point of time, and I think it's still very, very competitive. So for the work on Mpom, we decided to build on top of Mpom. And the first question we had in our mind was, given that this model is already trained on internet scale data, how much clinical knowledge does it encode? And so to do that, we subjected the model to the questions on the USMLE dataset, and we decided to look at the performance. And immediately we saw that there was a very big jump in performance compared to other standard models at that point of time. So the previous state of the art was around 50% accuracy, and Mpom was already performing at like 67.6%, which was beyond passing score. And so this was the first AI system to do that. And I want to anchor on it for a second because medical question answering has been a long-standing grand challenge. For several years, for several decades, researchers have been trying to solve this problem. And to get an AI system that reaches this level of performance has been a dream for many. And to be able to do that, I think, is a milestone that we all kind of need to appreciate. So that was great, and we were very happy. And then we also looked at the performance on other common benchmarks, such as MED-MCQA, which is Indian Medical Entrance Exam questions, PubMed QA, which is medical research questions on PubMed articles and abstracts, and then MMLU clinical topics. And again, over here, the model was performing very well out of the box. It was beating other systems, often by a wide margin. And then we looked at this model performance across scales. And what we were observing was there was an accelerated performance improvement as we scaled the model from 8 billion to 62 billion to 540 billion. And so this kind of suggested that the ability to answer such medical questions or reason about it may be an emergent phenomenon, which kind of emerges as you scale up these models. So the question was, are we done? And when I asked this question, probably the answer is also very obvious. We are not. And so the key insight for all our work over here was that human evaluation was key to revealing what are the flaws or limitations of these models. So Mpom, you can think about it as a general purpose model just like GPT-3 or ChatGPT or GPT-4. And out of the box on benchmarks such as USMLE, it was performing really, really great. But if we had not subjected the model responses to more rigorous and detailed evaluation, we would not have been able to uncover the limitations over here. And so that is the key, I would say, contribution of the work on Mpom over here. And so when we did that, we found that the Mpom responses often were not agreeing with scientific consensus, or were producing unsafe or biased or harmful responses. And I'll come back to the quantitative results in a moment. But the challenge was we needed to then align Mpom to the requirements of the medical domain. But again, the challenge over here is we don't often have enough medical domain-specific data. So you need a data-efficient alignment technique. But fortunately for us, several other researchers at Google had come up with this technique known as prompt tuning, where you freeze most of your LLM, but then add a small set of additional parameters, which you call soft prompt vectors. And then you use standard backpropagation techniques to just learn that set of parameters. So this is extremely data efficient because you're only learning a small set of parameters, but it's also compute efficient because, again, you just you're just working with a small set of parameters over here. So you can do this in a collab in a few hours, and it allowed us to iterate really, really fast. And then one of the other nice things about this was the ability for a model to do well with prompt tuning seemed to be also an emergent phenomenon. So we did that, and so we needed some expert demonstrations to be able to train this model. And so we turned to our panel of clinicians, and we asked them, OK, how would you answer these medical questions? Give us some demonstrations. And so they gave us many of these examples, and we curated about 100 to 200 of them, and then we instruction prompt tuned the model. And so the final model, Mpom, is basically Mpom, which is frozen, with a small set of additional prompt parameters, which we were using over here. And so this is the final model. And so the question was, OK, now how well does this model do? And again, the first thing we looked at was the performance on MED-QA USMLE. And we did not observe any degradation in model performance compared to Mpom. So that was great. And again, pardon me for anchoring on this result on USMLE again, because I think this is a big deal. The fact that we made so much progress and we have systems that can reach expert level performance on, passing score performance on these benchmarks, I think that's a pretty big deal. So that's great, but the key question was, okay, on axes such as safety, bias, harm, how well does Mpom perform? And so that is where we were seeing like these big jumps in performance. And so when we were looking at, like, for example, agreement with scientific and clinical consensus, we were seeing that Mpom out of the box wasn't scoring very well compared to expert physicians. But then Mpom was like bridging the gap by quite a lot, and there was not a lot of difference in performance. So you can see that over here. And we saw similar stories on other axes as well. So when we looked at, for example, possible extent and likelihood of harm, again, Mpom out of the box was not great, but then Mpom was bridging the gap with expert clinicians over here. Same story again with bias and responses. And then when we asked lay users how helpful and useful the model answers were, again, Mpom out of the box, only 60% of the responses were considered like helpful or useful, but Mpom was moving up to 80%. But then you can see that there's still a 10% gap with clinicians. So this is great. I mean, so we have a model that is kind of on the way towards physician-level performance, but was not exactly there. So this is kind of a nice segue for us to think about Mpom 2, where we have now, I feel, considerably closed the gap with expert physicians in terms of performance on medical question answering. And so under the hood, Mpom 2 is basically just three things, I would say. One is we switched our base model from the Pom family to the Pom 2 family. The next aspect was now we had more data, so we could do end-to-end fine-tuning of the LLM. And then the third thing was we had a better reasoning technique or a or a prompting strategy, which we like to call ensemble refinement. And then the big thing, again, with all our work in health AI or medical AI that we've been doing over the years is we, again, stress on evaluations. And again, so now we went one step further. And so we had another evaluation data set that we call Break Mpom data set. And so over here, we were assessing the model in terms of its ability to answer questions in topics such as obesity, suicide, mental health, where if you produce the wrong answers, it may amplify existing disparities or lead to like more bias or just through medical misinformation over here. So we wanted to ensure that the model was not doing anything harmful over here, especially on those sensitive topics. And then we also finally did a side-by-side comparison, comparing Mpom answers, Mpom 2 answers, and physician answers, just to see, okay, which ones were preferred. And so a bit more detail on the self-refinement, ensemble refinement strategy that we had. Over here, what we essentially did, we gave the question to Mpom, asked it to generate like 10 different reasoning paths or answers, and then we generated, when we used all those generated reasoning paths and put that back into the model, and then asked the model to come up with the final response. So it's a very simple strategy, but it's a two-step strategy that we used. And so when we looked at the performance of Mpom 2, previously I said Mpom was reaching passing score on USMLE. Now the performance moved up to 85%. So it's another big leap, and 85% accuracy on USMLE is what expert doctors produce. So we were like clearly now getting into this performance territory of expert doctors, which is great. And when we compared Mpom 2 answers to physician answers, previously with Mpom we were seeing that physician answers were better, but now we were seeing that on 8 of the 9 axes, we can with a lot of confidence say that Mpom 2 answers were preferred over physician answers, and this was by another panel of physicians. And then when we looked at the adversarial questions data set, which is on the right over here, we see that there is a big difference between Mpom 2's ability to produce like safe answers to these questions versus Mpom. The quality of these answers was significantly better. And finally, when we asked like non-expert lay users whether they considered Mpom 2 answers helpful, they said yes, and often they said the answers were more helpful even compared to like physician answers. So here's a qualitative example, and you can see that there's a big difference in quality. So the Mpom 2 answers were often more complete, more factually accurate, and often less prone to missing important information. And so these are all the important or key axes that I would say with respect in the medical domain. And here's an example from the Break Mpom adversarial questions data set. So you can see that this is a sensitive topic over here, and Mpom produces a more, I would say, rounded and complete answer. So that's all on Mpom and Mpom 2. We have some more exciting work coming up in the next few weeks. But I want to end on two notes. The first thing was Mpom started as a bottoms-up Google Brain moonshot. So a group of us decided that this thing should exist in the world. And basically, we had the program or the ability to do that at Google where we could will this thing into existence. And today, this is how it's going. It has received a lot of mainstream press coverage, and a lot of major investors and key opinion leaders have been talking about this for a long period of time. But it's not just that. I mean, Google's often considered like a tortoise with respect to shipping these LLMs. But we have actually ensured that Mpom is now available to customers on Google Cloud, some of the biggest pharma companies, life sciences companies, and providers. But it's also important to do this in not just a bold manner, but also a responsible manner. So we're not just opening up access to the model, but rather we are doing this in a closed, high-trust setting where we can get the feedback, iterate, and improve. And then once we feel we are more confident, we'll broadly open up access to the model. So I think that's great. But so this is not an advertisement for my employer, but more I want to say, if there is something that you want to do, just go for it because you don't know what ends up on the other side. So there wasn't a lot of support for us to do it in the first place, but we just ended up doing it through this moonshot thing. So that's maybe one thing I would like to say. And then the second thing is, what is the North Star, or what is the end game over here? Where do we want to go? And so imagine a fully interactive a doctor assistant. Imagine something that basically is able to take up all the boring work in a doctor's life today in terms of, for example, generating documentation for insurance or referral letters or prior auth. It can do all those things. But it's also a trusted assistant that can integrate information from multiple different modalities, such as imaging, from health records, from genomics, which a lot of doctors today cannot interpret, and then surface accurate and actionable information at the right time so that the doctor can use this to up-level the standard of care and provide better care to the patients. So imagine a truly interactive, trusted, trustworthy doctor assistant. And then the second thing that I hinted at in the beginning of the talk, imagine a world-class doctor in the pockets of billions worldwide. That is, I think, our end game over here. And I feel that is really possible. And that is the best part about it. I think we know what to do. We know how to do. We have strong base foundation models such as Gemini, GPT-4, Mpom, everything. But they can't be used out of the box in the medical domain. What we need is this additional phase, which I like to call AI sent to medical school, where the model can learn the etiquettes of the medical domain. But once it does that, I believe we'll end up in this end state where we will have a trusted doctor assistant that clinicians can use. And hopefully that will bring back joy to the practice of medicine. And at the same time, we'll also have a trusted assistant for billions of people worldwide, a world-class doctor in the pockets of billions. So with that, I would stop. Huge thanks to my scientific soulmates, my teammates who have been with me on this journey, and to all of you for listening. Thank you. Cheers.